everybody, welcome back to lesson number 9 for abstract algebra. Today we're going to be discussing the intuition and proof of the first Sylow theorem. So let's get into it. So the main idea actually comes from, at least to build some intuition, comes from factoring numbers. So the idea is, let's say we take a positive integer, let's try 120. We do something called the prime factorization of 120, and that tells us some more interesting facts about the number, and we can use number theory to prove interesting things. So 120 can be factored as 2 cubed times 3 times 5. And this is the prime factorization. You know this very well, but when you think about it, it's really kind of splitting a larger integer into smaller groups of prime numbers. And then, of course, bringing those prime numbers to certain powers when you need them to be. This might remind you of the idea we introduced last time of p groups and p subgroups of p groups. So we can try to think of an analog to this when it comes to groups. Let's say I have a group G where the size of my group is 120. Then I can try to imagine splitting my group G into 3 subgroups, which I'm going to call H2, H3, and H5, where similarly as above, I get the size of H2 is like a P group where P is 2, and I get its size is 2 cubed or 8. I get the size of H3 could be 3, and the size of H5 could be 5. Now, to be fair, for this example, from Cauchy's theorem, we actually already know that H3 and H5 exist, because we proved that if P divides the order of a group, then there's an element of order P. But we don't necessarily know that there's a subgroup H2 here in G. So something we would want is we would want these subgroups to exist, and something that looks like G is isomorphic to H2 cross H3 cross H5, which is similar to writing 120 is 2 cubed times 3 times 5. Now, luckily, we can prove that these kinds of subgroups exist. In any group that has size 120. But unfortunately, we can't prove the latter condition, which is writing G as the product of them. Unfortunately, we can't guarantee that G is isomorphic to H2 cross H3 cross H5. So this is kind of unfortunate. You might imagine, there's many different kinds of groups that have order 120. I mean, it would be kind of crazy to then be able to claim that all of them can be written this way. So, no, this is not always true. But it is true that we can always find subgroups of these orders in a group of order 120. So let's try to generalize this a little bit to introduce some definitions, and then we're going to prove the first Sylow theorem, which is about the existence of these subgroups. Okay. So we'll do 2 definitions. So let's let G be a finite group. Finite group. I get that if P, which is a prime, divides the order of G, a P Sylow subgroup is a subgroup that has size P to the n, which is similar to like 2 cubed here, where basically that's like the highest power of the prime that goes into the order of G. So is a subgroup of order let's say p to the m, where p to the m plus 1 does not divide the order of g. So this is basically saying, like, the order of g equals p to the m times n, where p doesn't go into n. And so my subgroup, my p-Sylow subgroup, is any subgroup that has size just p to the m. So it's kind of like extracting the highest power of p possible. The same way you do with prime factorization. You want to find not just something of order 2 in 120, you want to find something 2 cubed, because that's the largest power of 2. That goes into 120. Okay, now some other helpful definitions. I'm going to denote the set S sub p of g to be the set of all p-Sylow subgroups in G. All p-Sylow subgroups in G. And similarly, I'm going to denote this number, n sub p of g. This is going to be an integer, which is just going to be equal to the size of this set. So n sub p of g is just kind of counting the amount of different subgroups. And we'll find that once we prove the later Sylow theorems, which will be next video, that this number will pop up and will actually be very helpful for proving facts about groups and their Sylow theorems and the structure of that group. Okay. So now let's get into the theorem. The theorem, as we kind of described, which is the first Sylow theorem, is the existence of a p-Sylow subgroup when p divides the order of the group. Okay. Which is, to write it out explicitly, if p, which is a prime, divides the order of g, then there exists a p-Sylow subgroup. You could also write this as n sub p of g is greater than 0. Okay, let's prove this. So let's first let the size of g equal p to the m times n, where p does not divide n. So this is kind of like, as we wrote before, if p is 2, this is like, writing p to as many powers as we can, and then there's some extra factor n to get to the whole group size. But you don't want p to divide n, because then I could write this as p to the m plus 1 times some k. So this is the highest power of p that goes into G. And now I'm going to define a set. So let's define the set X to be equal to all the subsets of elements of G. So these are not subgroups, these are just subsets, such that the size of the subset is p to the m. So you can imagine these are all those subsets of size p to the m, choosing p to the m different elements. It's not a subgroup, so keep that in mind. So we can now define a group action. So let's let G act on our set X, where for, let's say, S is some set in X, G dotted with that set equals just the left coset of it, which can also be written as GS for all S and S. Note this is okay because we're choosing elements of S to be inside of G. These are group elements. It's just S might not necessarily be a subgroup. It's just a subset of the elements. Okay. So that's kind of why this is a weird roundabout way of describing left cosets, because left cosets are usually described of subgroups, whereas S is not necessarily a subgroup, just a subset. Okay. So we know we can partition X, since we can partition it into orbits, since the orbits form an equivalence relation. we know we can partition x into orbits. So we're going to just choose some sets and then describe all of x as the union of those orbits. So choose S1 through SR in x such that we get x equals O of S1 union O of S2 union S2 union all the way to O of SR. And also in particular, we're going to choose S1 through SR such that these are all disjoint, and we get that the size of x equals the size of O of S1 plus all the way to plus O of SR. Okay, so this is our setup. The first thing we want to do is, now that we have this condition, we want to try to figure out how we're going to extract subgroups of G, because that's what we're after. We're after P Sylow subgroups. Now, if you remember from the orbit stabilizer theorem, we can relate the size of stabilizers, which are subgroups, to the size of orbits. So the theorem explicitly said the size of the stabilizer times the size of the orbit is the size of the whole group. So our attempt is going to try to describe the size of maybe some of these orbits. The first thing we're going to do to determine that is first the size of x. So let's determine the size of x. Okay. Well, we see x is just subsets of size p to the m. So we just get that the size of x is just the amount of elements in G, choose p to the m. You're just taking all the elements in G and choosing p to the m of them, which is, I can rewrite this as p to the m times n, choose p to the m. Now, if you happen to know this theorem, this is really great, but most of you probably won't, you can rewrite this by saying this is equivalent to n mod p. This is called Lucas's theorem. It's a combinatorial theorem that you can also prove using group theory. Lucas's theorem. It's very cool. So we've now basically taken our set x and determined something about its size, mod p. In fact, we know that p does not divide n. That's how we choose an n, such that p doesn't divide it, which means that this is namely not 0 mod p. So the size is not divisible by mod p. So I can take both sides of my partition mod p. This is going to equal O of S1 all the way to O of SR mod p. And I know that this is not equal to 0 mod p. But that means there must be an orbit whose size is also not divisible by mod p. Because if these were all 0 mod p, then this would be a contradiction. So I'm going to choose some set S, which I'm just going to call it S now, which is one of the S1 through SRs. So just choose one of them whose orbit is not divisible by p, where the size of the orbit is where p does not divide the size of the orbit of S. Okay. Now we've made some progress. We've described something about the size of one of our orbits. Now we're going to try to relate that to the size of its stabilizer. Okay. Well, we know from orbit stabilizer, I get that the stabilizer of S, which is a subgroup, times the size of its orbit is equal to the size of G. Well, the size of G is just p to the m times n. So somehow stabilizer of S and orbit of S multiplied together are going to have to equal p to the m times n. But if P doesn't divide O of S, then all of the prime factors have to be in here. All prime P factors. All of them have to be included inside of stabilizer of S. Because if not, then this would be a contradiction. We can't get any P's from O of S, so we have to get them all from stabilizer of S. This implies that the stabilizer of S has to equal P to the M times K for some K where we get that 1 is less than or equal to K is less than or equal to N. Since it's a subgroup. Okay, this is some progress. But remember, we're trying to extract P Sylow subgroups, which are subgroups of exactly P to the M. So in this case where K is just 1. So what we're now going to try to do is we've shown that the size of the stabilizer of S is greater than or equal to P to the M. That's what we just did. Now we want to show that the size of the stabilizer of S is less than or equal to P to the M. Because if we get this, then we can say it's exactly P to the M, and we get exactly what we want, which is a P Sylow subgroup. Okay. To do this, I'm going to define a map. So I'm going to choose some element in my set. Let's let H be some element in my set. It's also a group element. So define the map, which I'm going to call phi sub H, which just goes from G to itself, which sends G, phi of H of G, is just going to equal G times H. Remember, H is a group element, so this is okay. Now we get phi H is a bijection because it has an inverse. In fact, I can describe its inverse very easily. Phi H inverse takes G and sends it to GH inverse. You can see this very easily because I can take phi H inverse of phi H of G and I'll just get G back. So they're inverses of each other, thus phi H is a bijection. Okay. Well, what if I try to restrict phi H? Once again, I'm trying to learn something about the stabilizer. So what if I check phi H restricted to just the stabilizer of S? So what happens if I just let inputs that are in the stabilizer? Well, I get that phi H of G equals GH, but by the definition of the stabilizer, it has to make sure if H is in S, it has to still be in S after I multiply it. Otherwise, it wouldn't be a stabilizer. Which means that phi sub H restricted to the stabilizer of S is an injection into S. But by definition, this means that the stabilizer of S, its size has to be less than or equal to the size of S. We know by definition that the size of S is equal to P to the M, which is exactly what we wanted. So now we've proved finally that the stabilizer of S equals P to the M and is thus a P Sylow subgroup. It is a P Sylow subgroup. And that is the proof of the first Sylow theorem. Now I'll just end this off with telling you something about our first intuition, which is, if you're curious, there is a way to reconcile groups with this prime factorization idea. So let's let G have like this prime factorization. The first prime times some power, all the way to like the nth prime times some power. So this is kind of like the prime factorization. Then if G is what's called nilpotent, then I can write G as isomorphic to HP1 cross HP2 cross all the way to cross HPN, where the size of HPI is that P-Sylow subgroup. So it's equal to PI to the RI. And I recommend searching up what nilpotent means. You might remember, if you've studied linear algebra, there's also a definition of nilpotent. Search this up. And it's not necessarily trivial why this is the case, but it is an interesting proof if you would like to see it. So there is a way to reconcile groups with prime factorization. You just need this extra condition of G being nilpotent. And then you can write it as the product of its P-Sylow subgroups. Okay. In the next video, we'll try to prove the other Sylow subgroups and do some examples. Thanks for watching.